Every morning, 2 billion people open the same app before they leave. They type in a destination, a blue line appears, and the system somewhere makes this prediction, not just take this road, take that road, given what is happening in the city right now. This is the fastest way to get to there. This is Google Maps. In this talk, my team will take you through how Google Maps answers this question. How can Google Maps predict the fastest route when traffic changes in real time? We'll cover where navigation was before AI came in, the computational thinking that powers the system, the real world impact, and the lessons that transfer well beyond just a mapping app. Firstly, let's cover the scale. 2 billion monthly users, 249 countries, and ETA accuracy of 97%, with a mean error of 1.8 minutes. And in 2020, a partnership with DeepMind reduced ETA errors by up to 50% in cities like Washington, D.C., Tokyo, and Berlin. So why does this matter? Because traffic is not a static problem. A road clear at 8 a.m. can be gridlocked in 15 minutes for an accident that no one even accounted for. For a century, drivers navigated by memory and radio reports. The tools they had could not see the future. Google Maps changed what a navigation system fundamentally does. It turned a map into a prediction engine. And how it did is what the next 4 speakers will explain. Long will now take you through what came before and the moment that changed everything.
So now let's imagine that you are driving in 2005. There's a GPS device on your dashboard. You enter your destination and it gives you a route that based mainly on one thing, the shortest distance. But it doesn't know that there is an accident ahead. It cannot see the traffic were building up, and it cannot update the route while you are driving. So the ETA you receive at the beginning is basically the only ETA you get, whether it is accurate or completely wrong. So that was navigation before AI. It could describe your path but could not predict what would happen on that road. So let's look at this table. This table shows a fundamental shift in how navigation works. The shortest route now became the fastest predicted route. No congestion visibility became real-time, color-coded traffic overlay on almost every road, and traffic data, which used to depend mainly on sensors on major highways, now become much broader through crowdsourced GPS data. So in 2009, Android users have anonymously contributed speed data back to Google in real time. That means that Google Maps can understand traffic conditions not only on highway but across roads in almost everywhere. The result is extremely high in ETA performance for 97% accuracy, with a mean error of only 1.8 minutes worldwide. So now come to the next slide. The number 97% accuracy was not enough for Google, so in 2020, they partnered with DeepMind to improve one specific challenge. Road networks are not simple lines, they are graphs. So in this, they consider the intersection are nodes, the road are edges, and traffic on one road can affect many roads around it. DeepMind has used Graph Neural Network, or also called GNN, to model the road network as one connected system. Instead of predicting each road segment separately, the model looked at how traffic conditions spread across the whole network. So for example, a traffic jam on one road may affect a slow down the nearby intersection, affect connected street, and change travel time across in a much larger area. So the result was a 50% reduction in ETA error in cities such as Berlin, Jakarta, Tokyo, Sydney, and Washington, D.C. So in Sydney alone, negative ETA outcome dropped by more than 40%. So that's not a small improvement, that's a major breakthrough in the system that has already used by over 1 billion people. So the key insight is very simple. Road networks are not just separate road segments, they are connected systems. So you want to predict one part accurately, you need to understand the whole system, and that's why the computational come in.
Computational thinking, we define it as formulating problems and expressing the solutions in a way that a computer can execute. Google Maps uses 4 pillars of computational thinking. For each pillar, I want to show not just what it does, but what it actually changes. First is decomposition. Find the farthest road from A to B sounds simple, but behind the sentence is a very complex problem. We cannot solve the traffic of an entire city as one big problem. It is too complicated for a computer to handle efficiently. So Google Maps breaks the problem into smaller parts. It collects GPS signals, divides the road network into individual road segments, estimates the speed on each segment, predicts congestion, compares possible routes, and updates the route during the trip. The change here is clear. Instead of dealing with one impossible problem, Google Maps turns it into many smaller problems that can be solved. When these small solutions are combined, we get real-time routing across the whole city. So next, pattern recognition. Traffic is not completely random. It follows patterns. For example, Monday morning rush hour is usually busy. School areas often slow down around 7:45. Google Maps uses historical traffic data for hundreds of millions of road segments based on time, day, weather, and special events. But it does not only depend on history. When life conditions are different, live data can update the predictions. Users contribute around 20 million data points every day, so the system keeps learning and adjusting. The change is that Google Maps does not just react to traffic after it happens, it can predict traffic before we reach it. Thirdly is abstraction. Real roads are messy. They have different lane rules, wows, traffic lights, turns, and many small details. If Google Maps tried to model everything at once, the problem would become too overwhelming. So it simplifies the road system into a graph. Intersections become nodes, road segments become edges. The weight of each edge represents the predicted travel time. This is why graph neural networks or GNNs work well here. They can pass information through the road network and understand how a slowdown in one area may affect nearby road. The change is that a messy real-world road system becomes a clear data structure that algorithms can analyze very quickly. Finally is algorithms. Google Maps then uses algorithms to find the best route. Modified Dijkstra and A-star algorithms search for the lowest cost path, where cost means travel time, not just distance. Machine learning models predict the speed of each road segment for the next few minutes. GNNs help process the whole road network together, and every few seconds, the system checks again whether your current road is still the fastest one. The change is that navigation is no longer just calculated once at the beginning. It becomes the system that keeps adapting during the whole journey. The route you follow is constantly updated based on the latest traffic condition. So, to summarize, Google Maps works through 4 pillars. Decomposition makes the problem manageable. Pattern recognition makes it predictive. Abstraction makes it faster to process. Algorithms make it continuous and adaptive. Each pillar matters, but no single pillar is enough by itself. Together, they create something that a paper map or an early GPS could not do: real-time, intelligent, and constantly updated navigation.
Now let's talk about impacts with 4 numbers, and each is real. 1 billion kilometers driven daily by Google Maps worldwide. 67% smartphone users who prefer Google Maps as their primary navigation tool. 50 million map updates pushed every single day. $400 million, the annual cost savings from UPS route optimization system. So let me put each in context. Before AI navigation, strategy was guesswork. I know the highway is bad on Mondays, so I will leave early. But today, live congestion overlays before you leave home. ETAs that update mid-journey, departure time recommendations, alternative routes the moment an incident is detected. The shift is from uncertainty to informed decision-making for 2 billion people every single day. UPS Ariane use graph-based routing built on the same principles as Google Map. 100 million miles saved per year, 10 million gallons of fuel, 100,000 metric tons of carbon dioxide avoided, $300 to $400 million in annual savings. A 2024 upgrade to dynamic Ariane cut individual driver routes by a further 2 to 4 miles per shift across 55,000 vehicles. That is another 100 million miles eliminated annually because an algorithm found better paths. For Uber and Grab, ETA accuracy is a competitive parameter. A single minute of improvement per trip, multiplied across millions of daily rides, moves their revenue. Singapore's AI adaptive traffic signals, minus 22% intersection delays. Los Angeles AI traffic system is minus 12% average journey times. Stockholm AI congestion pricing, minus 20% traffic volume, measurably lower carbon dioxide. These are not convenience upgrades. These are structural changes to how cities move. Navigation shifted from where is the road to what will the road be like in 20 minutes and what should I do right now? And now, Chang will bring us to the lesson learned and why this matters beyond just Google Maps.
Every great technology teaches us something that transfers beyond itself. Google Maps has taught us 4 things. The first one is to decompose first. City-scale routing is tractable only because the problem was broken into subtasks. Decomposition is not organization. It is what makes the problem solvable at all. The second one is data requires algorithms to become useful. 50 million daily updates are raw materials, not answers. Value emerges only when those signals meet pattern recognition, graph reasoning, and machine learning. The third one is that fastest is not always the shortest. Redefining the object from distance to predicted time produces better outcomes than any improvement to the algorithm itself. Redefining the problem itself is problem solving. The fourth one is good technology changes how problems are solved, not just how well they are described. Like Google Maps, they did not improve the paper map, but it rendered it obsolete. But I would be dishonest if I only told you the successes. 4 risks cannot be ignored are: first one, privacy. Continuous location tracking at global scale. The second one is algorithm headering. Recommending the same route to thousands simultaneously creates the congestions that it aims to avoid. The third one is imperfect prediction. 3% of 2 billion users is 60 million trips where the ETA fails. And the last one is over-reliance. When the system fails, users with no spatial awareness have no fallback. However, these are not reasons to dismiss the technology, but there are reasons to deploy it more thoughtfully. The 4 computational thinking pillars are not unique to navigation. Waze and Apple Maps uses the same architecture. Uber and Grab apply dynamic ETA prediction at commercial scale. Singapore's LTA uses AI to manage traffic in real time. Stockholm's AI pricing cut traffic by 20%. UPS Orient, the 100 million miles, 10 million gallons, $400 million, built on the same graph-based reasoning. Computational thinking is a transferable methodology. Decompose, recognize patterns, abstracts, and then algorithmize. In any domain where data is available and the problem can be formalized, these 4 steps produce transformative results. Google Maps applied decomposition, pattern recognition, abstraction, and algorithms to traffic prediction. Before, navigation was static, a fixed path calculated once. After, navigation became dynamic, a continuously updated prediction of the fastest way to move around an ever-changing world. The key lessons, which is transferable to every domain where complexity and uncertainty meet, is this: computational thinking's value is not in describing a problem more accurately, it is fundamentally changing how the problem is solved. Google Maps didn't improve the paper map, but it changes what navigation is. This is the end of our talk. Thank you for listening.